One of the problems that researchers sometimes face when performing virtual screening experiments is how to tie together and automate all the multiple steps of their experiment, including ligand preparation, filtering, and docking. Schrödinger provides a tool within Maestro to help do just such a thing, and it's called the virtual screening workflow. It ties together programs including LigPrep, EPIC, QuickProp, and Glide. Additionally, it allows researchers to automatically string together multiple Glide calculations, docking top-ranked portions of their ligand libraries with increasingly accurate methodologies. To get started with the Virtual Screening Workflow, or VSW, we'll head up to the main Maestro menu bar, click on the Workflows item, and then choose Virtual Screening Workflow. Here in the Virtual Screening Workflow interface, we see three tabs: Ligands, Receptors, and Docking Options. VSW allows you to run an automated series of sequential calculations that proceeds in essentially the order that you see it presented in the interface. From the top down in each tab, and then left to right across the tabs, the options that you see correspond to the jobs that VSW will run. Obviously, the first step is to specify which ligands we'll use as input. To do so, we'll click on the Browse button, which opens up this file browser that I'm using to select the ligand file in my working directory. In this example, we're only using a single input file that contains multiple structures, but it's possible to use more than one multiple structure file by using wildcard characters in the input ligand file field. Alternately, you can supply a plain text file that simply contains a list of multiple file names. It's important to have unique naming conventions to keep track of our docked ligands, so one of the nice things that VSW allows you to do is to create unique numeric titles using this default setting here. Alternately, we can click here to title the ligands using one of the available properties in this drop-down menu. Any structured properties contained in our input ligand file are available here, so if you want to keep track of your compound using a vendor ID property, for example, this is where you would choose to do so. If you want to retain only a specified list of compounds for docking, you can create a plaintext file that contains a list of the desired compound names and supply it here in this field. Whenever you begin with compound libraries that consist of 2D structures, you should ensure that you have the Prepare Ligands option turned on here. This will tell VSW to use the program LigPrep to generate low-energy, 3D, all-atom structures suitable for docking using the input files you've provided. Many of the options here are similar to the standalone LigPrep interface. The first option, to regularize input geometries, will create a one-dimensional SMILE string for each input structure, and then use that 1D file to create a full 3D structure. Glide's systematic conformation generator may produce slightly different results when starting with somewhat different input geometries, so this option is helpful if you intend to repeat docking experiments in the future and wish to ensure that the same compounds always have the same input geometry. Ligand preparation will also enumerate energetically accessible ionization and tautomeric states at biological pH, because it makes good sense to dock the compounds as they would actually appear in nature. By default, it also creates multiple stereoisomers from a given input structure if the chirality is ambiguous. These default settings should be reasonable for most cases, but depending on your particular experiment and setup, there are a few settings you may wish to change. If you have access to the program EPIC, be sure to generate your pH states using EPIC, which is more sophisticated than the ionizer utility. Additionally, if you intend to dock large macrocycles, you'll probably wish to use Macromodel for enhanced ring sampling. Finally, the Ligand tab also provides options for filtering your ligand library prior to docking. Not only does this save time during the docking calculation, but it's also useful for eliminating compounds that aren't especially drug-like. You can perform atomy predictions using the program QuickProp, pre-filter by Lipinski's rule of 5, and remove ligands with reactive functional groups. You can also retain only ligands that match specified criteria. To set up our matching criteria, we'll simply click on the Criteria button, which opens up the Filtering Options window. Each of the three tabs in the Filtering Options window is essentially similar. In this case, we'll filter by molecular weight. We can do so by clicking on the General Attributes tab, choosing molecular weight, and separately setting the upper and lower bounds for molecular weight. Any ligands that don't meet these specified criteria will not be docked. If you want to use the same criteria repeatedly, it's possible to read in a plain text criteria file using this button here. Filtering is done using the LigFilter utility, so if you've previously created any filter criteria file for that standalone command line tool, it will also work here. Once we've specified our input ligands and how they should be treated prior to docking, we can click on the Receptors tab to choose which receptor models we want to dock against. Glide docking jobs are a two-step process. First, grid files are created for the receptor active site. Then, ligands are docked onto that grid file. Here in the VSW interface, we can either use pre-computed grid files, or we can generate them using a structure in the Maestro workspace. Many of the grid generation options here are very similar to those in the standalone Glide grid generation interface, so if you're familiar with the standalone interface, these options should be largely self-explanatory. In this example, we'll use pre-computed grids. The VSW interface allows you to specify multiple grid files so that you can perform ensemble docking against multiple receptor structures for your target. First, we'll click on the Browse button to load in our first set of grids. If you want to enable the optional docking constraints associated with your grid file, you can simply click on the Constraints button. We'll enable the desired constraints by clicking on the appropriate toggles, and we can also set how many of the specified constraints need to be matched. It's also possible to enable ligand core constraints, just as you would using the standalone Glide docking interface. We'll accept our constraints by clicking on the OK button, and keep the default name here, and the glide score offset here. The glide score offset can be used to penalize or reward ligand hits from one receptor model relative to another simply by weighting the glide score with a positive or negative term respectively. Now we'll add the above grid file to our list of receptors for docking by clicking on the Add button. Then we'll add another grid file by repeating the process. We'll click on the Browse button, choose our receptor, enable constraints, and add the grid to the list of receptor models we'll be docking against. If at any time we want to change our receptor settings, for example if we wanted to turn off the constraints that we enabled, we would just highlight the appropriate entry in this table, click the Edit button, make the changes, and then click the Save button. Receptor models can also be removed from this table using the Remove button. Now that we've specified what ligands we'll be docking, how those structure files will be processed prior to docking, and which receptor models they'll be docked against, all that remains is to set a few docking options. Click on the Docking Options tab to finish up. If you're familiar with the standalone Glide docking interface, much of this tab should look familiar to you. And again, as with the Ligands tab, this tab has a number of options listed from top to bottom that will dictate, in sequence, a series of calculations that the virtual screening workflow will automatically execute. In this case, those calculations are a hierarchical series of docking experiments. This is extremely useful if you have a large ligand library, but relatively limited computational resources. Suppose you were beginning with a 1 million compound library, but only had resources to dock 10,000 ligands using Glide Extra Precision, or XP, the most accurate docking and scoring mode in Glide. With VSW, you can dock the entire million compound library using Glide's extremely fast, high-throughput virtual screening, or HTVS, mode. VSW can then redock the top 10% of HTVS hits, or 100,000 compounds, using the more accurate Glide Standard Precision, or SP, mode. Finally, the top 10% of SP hits, or 10,000 compounds, can be docked using XP Glide. The upshot is that rather than using Glide XP to dock 10,000 compounds pulled at random, with VSW, Glide XP is instead used to dock 10,000 of the most promising compounds from your million compound database. The exact settings you choose for ligand pass-through rates will most likely depend on the size of your ligand library and the availability of computational resources to you. At the top of the Docking Options tab, we have the ability to filter out extremely large or floppy ligands and also to scale ligand van der Waal radii. Then, to enable the desired steps in the hierarchical docking process, we need only check off the desired boxes. For example, if you were working with a smaller ligand library and wanted to perform only SP docking followed by XP docking, we would uncheck the option for HTVS, but leave the SP and XP options checked. In this example, though, we'll do all three steps. You can see that for HTVS and SP, we can choose what top ranked percent of the ligand library or what number of compounds gets passed on to the next step to be docked using a more accurate Glide mode. We can also choose what enumerations of these compounds get passed on. If you recall back to the Ligand tab earlier, we were preparing our library so that a single compound will be docked using whatever ionization and tautomeric states are predicted to be present in significant amounts at biological pH. For the fastest docking mode, HTVS, by default we'll pass all ionization and tautomeric states for top-ranked ligands onto an increasingly accurate Glide docking mode. But after docking with the more accurate SP glide, by default we'll only pass on the good scoring states the glide found for any given compound, since we can have greater confidence in the results. When performing ensemble docking with multiple receptor models, at each stage of the docking hierarchy, the entire set of retained ligands is docked against all of the receptor models in the ensemble, regardless of which receptor model previously ranked the ligand most favorably. You'll also notice that for glide SP and XP, the default is to flexibly dock and score the ligands passed on by the previous step in the docking hierarchy. However, it's also possible to position and score the rigid ligand geometries produced by the previous docking run to refine, relax, and rescore poses produced by previous steps, or simply to rescore ligand poses from the previous docking run. Lastly, for the glide XP step, it's also possible to generate multiple input conformations for the purposes of performing more exhaustive conformational searching, to write XP descriptor information for use with the XP visualizer, and to post-process results with Prime MMGBSA. To execute our entire workflow, we can click on the green Start button and launch it as a single job that will automatically distribute the necessary number of subjobs across the requested number of processors. We can also write the input files to disk for future use. Finally, if you want more information about any of the settings or options in the virtual screening workflow interface, you can click this Help button at any time to bring up help documentation in your web browser.